In terms of what these threat actors are after, it's pretty simple. There's kind of three things we see a lot. Credential theft, so developers have access to a lot of attractive targets for these attackers, like, I don't know, data or code, right? Very simply, so a lot of times we'll see them going after API keys or credentials like this. Resource misuse, so things like crypto miners. You install some package and it's got an embedded crypto miner, and so there you go. Or thirdly, something like SolarWinds. So it's a downstream compromise where some downstream client of a package is being targeted. And so, yeah, maybe the choice to use open source is more complicated than it might seem at first, security-wise. So we'd like to feel confident in our decision to do so, and so that's kind of what we'll be talking about here.
Okay, so detecting malicious packages with Gardo. We're going to explain a little bit on how we are using this CLI tool, which is a tool that we created in Datadog internally for scanning PyPI and NPM ecosystems. So basically, we use Gardog, which pulls data from the package published in PyPI or NPM, and this tool makes use of two kind of analysis. One called metadata analysis, which is basically the detection of some patterns present in the characteristics of the package itself. Imagine something like the registration email address of a maintainer, right? In this case, it can be used in a disposable email address, and that's this kind of detection. On the other hand, it makes use of another type of detection called source code analysis, which under the hood we are using two tools. One is called Yara, which makes use of, is very good for indicator for compromises, such as domains or IP addresses. For instance, in this case, we can use like this kind of detections in a Yara rule. Also, we are using SEMGREP, right? This is another kind of tool that detects kind of a semantic analysis for, and it's very good to detect like kind of a behavioral patterns in the code, right? For imagine this, we are using, it shines really well with the detection of, for example, execution of base64 payloads. So this sample execution of Gardog, this tool, you can see those are the rules that detected in a real package in NPM. A couple of things to notice of Gardog is that it allows you to use JSON and Serif format outputs to do a more automated analysis on the outcome. And also, one thing to notice is that Gardog, it doesn't give you any a final decision if the package is malicious or not. One thing to notice is that it just raises the risks on the package. Okay, the actual decision has to be taken by an actual triager at the moment. So this is how we use internally Gardog in Datadog. Basically, we implemented a set of autocrawlers that are basically crawling the repositories PyPI and NPM. We roughly, you can imagine we have like 300K for PyPI and 75K of PyPI. 300K of NPM packages and 75K of PyPI packages a month. And then we scan these ones with Gardog, and the findings that we were talking about are filtered then with a set of behavioral patterns and a combination of machine learning techniques. Okay, to have an idea, we're considering having like a 0.6% of suspicious or interesting enough packages to further analysis. The further analysis, which is the triage stage, is conducted by a human, right? And if confirmed, then the malicious package the sample is uploaded to a public repository called malicious public dataset.
Great, thanks. So yeah, now we'll just kind of go through, we have 4 kind of common strategies we see these threat actors using, and we'll just kind of use some of these packages we've been finding with GuardDog to kind of support kind of the case we're making. So the first is to target popular packages to get at their developers. We were saying earlier, developers, these attackers, so how do you get developers? You go after the packages they want to use. So basically, there's kind of 2 ways you can go about this. If you're the attacker, you can publish a new, already malicious package, or you can seek to take over an existing package. The first case is very easy. You can just upload whatever you want, like NPM, say, but it's not a very efficient strategy because like 10K packages get uploaded to NPM every day, so nobody knows your package, right? So if you're an attacker, how do I get people to take notice of my package? And so the way they often do this is not very sophisticated, right? You just kind of try to affiliate the malicious package with some targeted package, usually by like a naming trick. So we see a lot of combo squatting where if I'm targeting requests, I could do something like pi requests or something, or typo squatting where the name of the malicious package is a typo of the targeted package. You can see like that. Not very sophisticated stuff. On the other hand, package takeover is a lot more lucrative because these packages already have developers that use them, but it's harder for the attacker. They have to perform some kind of compromise to get it to work. And so this could be like compromising the maintainer credentials, a malicious PR, other things like that. So if we go back to our architecture kind of overview, this could take place like anywhere, right, at any stage of the pipeline, depending on what the attacker is trying to do. So here we have an example that we found in the past year of a name squatting attack or a combo squatting attack. So on the left we have a legitimate NPM package, and on the right we have a malicious one from a threat actor we've called Tenacious Pungsan at Datadog. So it's a DPRK affiliated threat actor, and we use like the national dog breed of the nation to like name the threat actor. So the Pungsan is a DPR. It's from dog from North Korea. So you can see very simply passports.js. Otherwise, like if you look at the readmes, they're exactly the same, although like the graphic didn't load on the left. But you know, you just copy the code, backdoor it, and upload it with a similar name, right? Not very sophisticated. On the package takeover side, the stuff tends to be more interesting, right? There was, right at the end of 2024, there was a notable package takeover instance for this Python package called Ultralytics, where they were running like a vulnerable GitHub action on their repo. You can see in the pink box, like the branch name is used like unescaped in a shell command. And so this allowed an attacker to submit a malicious PR with a crafted branch name, which like ended up running a shell script in the context of the GitHub action. And so they were able to like exfiltrate the PyPy publish token and upload some malicious versions to PyPI. There's a great analysis of this attack at that blog post. And so like package takeover is complicated, but the name squatting stuff is very simple to avoid by just like doing the simple obvious checks. So our advice would be just to use some simple guardrails to minimize the consequences of simple mistakes like a typo. In our research in Q4, we found that at least 70% of the malicious packages we triaged were using some kind of name squatting or targeting some other package. So if you're an end user, if you're like a user of an open source package, just make sure you're spelling everything correctly, the simple obvious solution. To get around package takeover, you could use version pinning. Don't use like just the latest version of the package in case something happens. And then if you're lucky enough to work like at a company who can do this for you, or in some institution who would do this, use like an internal not copy, but sort of an internal version of the package repository with verified artifacts to kind of only pull things from. You'll cut off a lot of these kinds of problems that way. Meanwhile, if like for the package repositories themselves, I think we would suggest like introducing some kind of moderated publishing. So simply like not allowing people to publish on typo squats of certainly prominent packages, but ideally all packages. Whether it's some kind of verification of like this code looks too similar to an existing package, like no. And then also, post-compromise, take those package names out of circulation and replace them with security placeholders so that people who didn't update their dependencies don't get reinfected.
Okay, now we're going to talk about the next strategy used by threat actors, which is called exploit developers via install time hooks. So install time hooks is a method that can be used in the packages like PyPI or NPM that trigger at install time, right? This is a very like visual way to exploit something. So how this actually works in the wild? I wanted to go over with an example. So let's say I'm an attacker. and I publish two set of artifacts. One to NPM with a malicious payload, very visual, I don't know, with the install execution. And another, like a sample repo into GitHub for doing whatever. This GitHub repo does have non-malicious behavior whatsoever. The only thing that it has is it has like a dependency to the npm package that was published before. Then the user, legitimate user is lured into download the package, right? There are a number of ways how threat actors can achieve this. One of the favorite techniques implemented by DPRK threat actors is to use them as a job interview, right? Hey, I need you to do this job for me. You have to do this test it out. You have to download this code and execute it. Then, bam, this code is pulled from the NPM and triggered. So if you look at, again, into the architecture diagram that was shown before, this attack goes over in the use of compromised dependency and use of compromised package parts. And in here we can see an example of how this self-deleted initial attack access vector was used by the threat actor stress function. Again, in Datadog we name the known threat actors. Function in this occasion goes after the dog breed of the country that was the threat actor representing. And so we can see here that it's executing the reference.js file, which in this case downloads using curl, downloads a DLL, uses the run-DLL32 binary to be a trusted binary execution of the DLL code that is downloading. This is a technique very used again by this threat actor. Another example from in this case from PyPI, from the Lapardexos package. In this case was from MUT 8694. MUT stands for miscellaneous unattributed threat. Basically, this is the way we name threat actors that are not belonging to a known or a nation-state actor, but we can cluster the attacks into one specific cluster. So as you can see, he's overriding the installation process, and in the file in the installation process, he's also using PowerShell to download a binary and execute it. This time was a stealer. So what can we do with this? Be wary of install time hooks, right? This sounds obvious, but it's I mean, threat actors often disguise this or cover this under like downstream attacks, like dependencies. So the attack is not so obvious, right? So one recommendation or mitigation we can say, first of all, 85% of the malicious packages we observed during Q4 were using this kind of attack. So this is important, right? For package maintainers, we can say limit the usage of install scripts as much as possible. We see times and times again that developers are like using the install time hooks for greetings. Hey, thank you for installing this package. I mean, okay, but there are other ways to achieve that, right? For end users, if possible, completely disable install script. For a PyPI, you can use wheels. This doesn't implement setup like installation scripts. But for NPM, it probably will break stuff. You can leverage on Guardo for that matter. Guardo is the tool we showed earlier. So for package repositories, warn, you can use, this package is using this. Probably not very helpful, but surely it can help in some cases. And also perform regular audits if packages are using this.
Okay, great. So the third thing we see a lot is the use of obfuscation to kind of hide what they're doing. So if you're a threat actor and you want to deliver malware via NPM, a problem you run into right away is that everybody can see the malware. So you need to hide it in some way. speaking of NPM, like one thing we see a lot is the use of this obfuscator called obfuscator.io, which produces this garbled sort of looking text here at the bottom. What it does is it takes the input code and like one thing, it replaces the variable names with like random ones. It removes the formatting, but then it also kind of packs the code in a certain way where it's getting unpacked at runtime and actually being executed. So it makes it difficult to read and difficult for static analysis to help you on. Fortunately, it's relatively easy to partially unobfuscate it or deobfuscate it, and so indeed that sample we were just looking at, when you deobfuscate it, it deobfuscates to this in part. So this is 2 screenshots from an info stealer called Beavertail, which is a DPRK associated info stealer. So, you know, on the left and right we have like a second stage being downloaded, and then on the right we have some data exfiltration. So again, this you'll need to be on the lookout if you're like the user of a package or if you're using a package to build something. Here's just another example of this. On the Python side, it tends to be a little different. So we see a lot of like decode and execute patterns, so base 64 or decompression or decryption or like character encoding stuff. And it just goes to the point that like ecosystems have their own kind of obfuscation tactics or techniques that people use. So the obvious recommendation is just say no to obfuscation. There's no good reason to distribute open source code that's intentionally difficult to read. So don't write it, don't use it, don't host it.
And the last strategy we're going to see is the minimized exposure by using a second stage payload. So this is an example of how the second stage payload is used. If, in case you are not aware, malicious actors are using this thing that is called second stage payload, which is deliver one small portion of like just a downloader of the real stuff. So you only have to deal, like for instance, in this case we're seeing the response example, which lures the victim to install the package as we discussed. It runs automatically the script and then downloads the DLL and then runs it, right? The point here is that the DLL has the actual payload. The only thing that was like in the package was the link to download it, right? Again, in the architecture diagram, this goes into the use compromise dependency or used compromise package. Here we see an example of using PowerShell to download a stealer. Again, the malicious payload is hosted in GitHub, not in NPM nor PyPI. Another example, using, again, obfuscation, the method that Ian was talking about, is concealing a bash script that installs a service to run a miner. So what can we do with this? Make sure your code is behaving, okay? How easier said than done, right? So for package maintainers, we can say avoid using external runtime downloads. It's harder. It's not always able to do this, but in several times we've seen that it's overly used, right? So for end users, examine if a package downloads has downloads patterns. Like again, this is harder to achieve, but Guardor can help out here. Otherwise, you can use a container to somehow mitigate the data exposure of the host. Else, you can try.
Yeah, so this thing called supply chain firewall. So at the tail end of last year, we released this open source package that basically is just a drop-in CLI tool to like filter your npm and PyPI install or pip install commands. Excuse me. So it'll inspect the install targets. It'll check them against lists of known bad packages, or like if there are vulnerabilities, it'll let you know about that too. And then yeah, it'll kind of, if you set up your environment the right way, it'll passively scan all of your commands. So there's the pip install command if you like, and yeah.
Okay, some final thoughts. For package maintainers, don't be shady. That means leave the bad guys do the weird stuff. Try to do like the most obviously benign code behavior, right? For end users, don't be an easy target. If you're installing something that you're unaware of what it is, do your research, check, test, probably isolate it, right? And for package repositories, lastly, increase the barrier to entry for threat actors. It's really, really easy for threat actors to publish bogus or malicious packages. So there are a lot of good improvement opportunities there to prevent that for the techniques we saw today. And yep, that is it.
We have 2 minutes for questions.
Yep, sure. So go ahead, sorry.
Yeah, thank you very much for the interesting talk. I have a question about the supply chain firewall because you said that it checks against a known list of malicious packages, and oftentimes malicious packages are removed from the official package repository. So, for example, on NPM you have a security holding packages. So I wanted to ask you, like, what is actually preventing the supply chain firewall if you're somehow already prevented from the actual package?
Yeah, that's a great question. So the short answer is that's kind of it. It's the very early days for this tool. We hope to. I'm sorry. The question was, what if packages are being taken down quickly from these open source ecosystems? What is supply chain firewall actually doing for you? So you're right. Right now, it's kind of only good for, on the malicious side, for things that are known to be malicious, right? So if it's been taken down, the threat has been kind of neutralized in some sense. These things can like loiter around in different mirrors and things maybe. It also consults osv.dev, so there's like a secondary function for pointing out vulnerabilities. We hope to integrate like scanning capabilities into the tool later on, maybe facilitated by GuardDog. Yeah, that's where we are today.
I think we're out of time. Maybe one question.
Sorry. Nice talk. You focus a lot on the package managers. Any thoughts about, for the supply chain, you also mentioned quickly the developer environment. Any thoughts about all the crazy plugins that are out there?
Sorry, come again.
You focus a lot on the supply chain and the package part, but almost nothing on the developer place. So do you have any thoughts about the plugins in the developer environment, like the Visual Studio Code plugins?
Do you want to take it?
Yeah. So if I understood correctly, if it's like we are focusing a lot of on the package maintainer, but if there is something we can do on the developer side. So basically we're giving like a couple of good tips for every single parts, right? For instance, for the developers, we said something about like try not to run or to provide obfuscated code, right? But this is like this is something like it has to be implemented. This control has to be implemented in all parts. Like we can say to the developer, hey, don't obfuscate your code. We can detect it. But if package maintainers or repositories are not preventing to upload to open source repositories obfuscated code, it's like that's pretty much everything we can do, right?
I think we're out of time, so thank you.
Okay. Thanks. Yep.
Is that your cable?
Nope.
Good.
Okay,
Great.
so you got it there.
All right.
I'm not sure if you will mirror it or...
Yeah, I'll just mirror it.
Yeah, so that's...
Yeah. What's up?
And I will be holding up and counting down to 20 minutes.
Okay.
So you will have time for questions.
Great. Thank you.
So we are on time. Please take a seat if you're not sitting. And welcome, William.
Hey, everybody. Thank you for staying so late for my talk. I know it's pretty late, so I appreciate it. Today I want to talk a little bit about a tool that I built a couple months ago called Zizmore and how I've been using it to hunt for GitHub Actions bugs and how you can use it as well. So just a little bit about myself. My name is William. That's my website. Currently I'm an engineering director at Trail of Bits. But this is not a work talk, and these slides nor my opinions that I express throughout them are the opinions of my employer. And outside of work, I'm also a maintainer of Homebrew as well as a member of PyPA and a contributor to PyPI and a few other things. So you'll see me possibly make reference to some of those. And then if you want, that QR code has these slides. And so if you want to follow along, there's some parts where you can try in real time the things I'm going to show you, so you can try to exploit them yourself. But actually, let's skip that. So let me do an intro to GitHub Actions. I figure probably, actually a quick show of hands, how many people have used GitHub Actions in this room? Okay, overwhelming majority. So I'm not going to do too much of a intro, but basic version, it's GitHub CI/CD offering. It's free for open source. It costs money otherwise. It's a bunch of YAML hell. Workflows are sort of top-level units of execution. They contain jobs. Jobs run on VMs. VMs contain jobs that have steps, and each step is an independent sequence of shell commands or recomposed actions, which contain themselves other actions or shell commands. These can be checked out from other repos. So actions checkout actually checks out the actions checkout repo and runs code from that repo. Those actions themselves are also YAML hell. They define reusable operations that you can share between repositories. There are official ones, which are generally under the actions namespace, as well as third-party ones, any public or private repo on GitHub, as well as local actions, as in you can call an action that is defined somewhere in your own repository if you have it checked out within your job. These have full generality. They can run code, they can run other actions, etc. And importantly, they run in the context of the job that executes them, meaning that any secrets, credentials, etc., that you give that job, the action also has. And also, sort of importantly, as we'll see later, they have full access to the job's runner state, which includes the file system, which contains all kinds of interesting and useful things, as well as other processes running on that VM. So bottom line, GitHub Actions are arbitrary code execution as a service. That will come up in various important ways throughout this talk. It's a very powerful system, GitHub Actions. GitHub Actions, it plugs into the broader sort of permissions model that GitHub offers. Every workflow runs with a latent secrets GitHub token or GitHub token, depending on the context you're in. And by default, unless you opt into a more secure mode, this token has a lot of powers, including modifying the repo contents of the workflow, of the repo that contains the workflow that is loaded with it. If you are a workflow author, you can also up or down scope this credential at the workflow job or step level with permissions blocks, which tell that scope of action how many credentials it has, which it can't exceed with that default token. However, there's sort of some wonky behavior there, where permissions are inherited from parent job or workflow contexts if they're not set. But if they're explicitly set, they're shadowed. So they're not telescoping, they're shadowing semantics. And again, this comes up in important ways. So of course you can do things like on the right, where you have explicit read, write, or none permissions for each sort of scope, or you can set read all or write all, or you can do an empty object, which means give me no permissions at all. However, that still produces a token. That token just gives you sort of larger rate limits versus not having a token. Another way in which GitHub Actions is extremely powerful, which again will come up when we talk about the security aspects of all of this, is that it has this extremely powerful expression system. Most parts of the workflow or action definition scheme in YAML support expressions, which are defined via this like curly syntax where you put an expression in the middle. Sometimes you don't need those curly, such as in an if condition. These expressions have a lot of functionality within them. They can do math, they have control flow, they can encode and decode JSON, they can call a set of functions that are defined within the runner itself, etc. They can also directly, or rather, when you expand them, they expand directly into whatever context references them. So an if condition, an end block, a with input, or even a run body, which contains, obviously, shell script that you're trying to run. You can expand values directly into that shell script. At the core of the expression system are these things that GitHub calls contexts, which are really just JSON objects. When the runner is invoked, it is loaded with a set of contexts, and you can access those contexts sort of as if they were like JavaScript objects. So if you have a nested dictionary that has like secrets.github token, that gets modeled as the context secrets.github token in the expression syntax. And these contexts come from both static and dynamic sources. So the static source is something that you define sort of ahead of time for the runner to load. So that's things like the runner's configuration, as well as GitHub side state, so the event name, the event payload trigger that triggered the workflow. And then dynamic is things like matrix expansions. Okay, I realize I have way more stuff than I thought, so I'm going to kind of breeze through this. Even more powerful, you have these special variables. You can set environment variables, you can set the path, you can set variables between steps, and you can also set step summaries. There's also a special file system state, like event path and tool cache, and these are, again, useful in ways we'll see. So now let's talk about the security of all of that. So before I do that, why does any of this matter? Well, one answer is it's wildly popular and it does everything. It's the default choice for GitHub, meaning that millions of people use it. Pretty much everybody in this room uses it. As a corollary, it's used by developers with huge skill ranges, meaning that people who just want to get something done are using it the same way that people who are experts in CI/CD deployment. And it has this massive range of uses, including, most interestingly to me, people publish to PyPI, et cetera, using GitHub Actions, which means that the security of their package on those indices directly mirrors the security of the system that publishes them. So millions of users plus a really powerful and complex feature system means security fails. So let's break some of this stuff. Okay, crowd question. Find the vulnerability in this. What's the issue? Anybody know? Yep, okay. Template expansion, right? What we're doing is we're expanding the value of GitHub event pull request title directly into the shell context, which of course I can give it hello, semicolon, cat say password, and now I'm running arbitrary code. So again, the core thing here is this is something that the attacker controls. The title is an attacker control value that is loaded. Anybody can create a pull request on a public repository. If you put your title as hello, semicolon, cat say password, you're now running code in the context of the workflow that triggered it. That's baby steps. Okay, what about this one? We've quoted it this time. Does anybody see the problem? It's the same vulnerability. It's the same damn vulnerability. And the reason for this is going back to expressions. Expressions do not care about shell level quoting. Because they're injected by the actions runner before any shell processing happens, they're injected, there's no chance for the shell to reparse what you've injected. It's exactly the same thing as SQL injection. You can quote as much as you want in SQL injection, but if you're directly injecting the value, you can always inject an escape to the escaping. So in this case, our payload would be hello, quote, payload. And we get the exact same thing. So this is baby steps. Okay. Anybody see the vulnerability here? Okay, that's enough time. So it's nothing about any of the steps. All the steps are semantically correct. However, what happens is actions checkout, that step we call up there, the first one, it persists silently at the GitHub token by default. So when you run actions checkout, that context token that you use gets stored in .git config in the repo that you check out. Then, when you run actions build upload artifact with the current directory as the path, you have now persisted your credential to a public artifact, meaning that anybody who goes to download that artifact now has your credential. That credential is only alive for about 4 hours, if I remember correctly, but for 4 hours you've now leaked potentially a global write credential for your repository. Okay, still baby steps. They fixed this, by the way, but they fixed it by not patching checkout, but by patching upload artifact to ignore .files, which broke Python coverage. Okay, getting a little bit more interesting. Anybody see the bug in this one? You'll notice that we are no longer doing environment expression injection. We're now forwarding via an environment variable. So there's no more injection vulnerability there. Okay. Like I said, GitHub environment is one of those special variables. It's a file, but it's just a file, nothing special. However, we can write multiple lines to it at once. So in this case, if a user or an attacker submits a title that matches that expression before, that expression, because it uses the, I believe it's the P flag, it prints multiple times, once for each match. So in this case, we've injected two variables when we meant to only inject one. We've injected message equals foo and also ld preload equals hackme.so. And so now if you can put if you have write access to a runner, even if you don't have execute access, you've turned your write access into execute access, because ld preload will run in front of any binary that gets executed. So there you go. Okay, let's get a little bit more advanced. GitHub Actions has services and APIs and actions for saving and restoring caches. These are used and are critical for speeding up actions that pull a lot of things from public indices. These caches are keyed and it can be restored based on partial key matches. So for example, if you have your Rust dependencies, you want to restore from multiple different sources if you unfold from multiple places. And the way it restores when you have partial matches is it restores based on that partial match, but also sort of a privilege system of anything that's previously been landed in the upstream repo. So if you can poison that upstream cache, any downstream workflows that run will run with your poison cache. So here's the question: how does GitHub know which branch a cache restoration should come from? Well, the answer is the branch name is an implicit part of the cache key, and it's computed on the client side. How does GitHub Actions authenticate cache stores? Stores are authenticated with an Actions runtime token, which is injected into the runner. It's separate from the GitHub token. Combined, this is the perfect recipe for cache poisoning. We have the credential we need to inject cache entries, and we have a client-side controlled cache prefix, which we can tell the Actions cache service to cache with. There's no authenticated domain separation, in other words, between branches, which is hard to do because you would need then a way to do like delegated authority between branches, meaning the branches can collaborate with each other's caches. And all workflows in the repo that run with the repo's permissions have that Actions runtime token, which means that even a very, very weak workflow, one that has empty permissions, still has that cache token. And it's valid for 6 hours, which means it's not invalidated by run or teardown, which means you have 6 hours to effect your cache poisoning attack. So this was kind of my spoiled by the previous session, but Ultralytics is the perfect case study for this. Really popular machine learning vision model, 68 million downloads from PyPI, and they have many CI/CD operations that are intermediated by a bot account. Spot the vulnerability. It's the exact same one. It's our baby step vulnerability. They inject directly into the shell context with the user-controlled variable. This is happening with a pull request target trigger, which, unlike a pull request, runs with the upstream repo's permissions. So they've given this attacker upstream repo token permissions. The attacker sends a pull request with that title, which runs this payload, steals the cache token, and goes on to smash the cache with a bunch of entries, one of which eventually causes a malicious PyPI upload. So what's cool about this is that they didn't steal, well, later on they steal, but at first they didn't even steal the PyPI upload token. What they did was they poisoned the artifact that was used to produce the upload token. So this isn't visible from PyPI's system. So they do this, right? But what's great is, and the release is done fully on CI with a push event, meaning that it was pretty hard to notice until someone actually noticed the malware on their system. But, Ultralytics responds, mission accomplished. They have deleted they have, triage and everything. Several days later, it happens again. And the reason for this is that even though they fixed the actual cache poisoning vulnerability and the permissions, the insecure trigger they used, they did not revoke their old credentials. And so the attacker just stole the old credentials, which they never revoked, and did it again. So after you've been owned on GitHub Actions, please revoke your credentials. Okay, I don't have enough time for these takeaways. Please look at the slides. Okay, now I actually want to talk about the talk, which is hunting for bugs with Zismore. So demo time, you can do this yourself if you want, but here is Zismore. I'm going to run it without online audits because the Wi-Fi is kind of slow, and I'm going to run it against the 2 repos that the Ultralytics attack was on. And it's pretty fast, and there we go. This is just every case where the attacker could have injected. They only needed one of these, but, it's not so good. Okay, technical details. Zismore is a typical audit tool architecture. It has a preparation phase, an operation phase, an aggregation phase. And then the output is like this Rust-C style diagnostic, where it'll tell you what span caused the vulnerability. Individual Zismore audits are implementations of this audit trait, has sort of standard stuff. And then there's various ways you can define an audit. It can be over a workflow, a composite action, or the individual steps or jobs within a workflow if you only need that level of granularity. There's actually a new one too. There's audit raw, which you can give the raw input to as a string if you need to do just like basic, really, really, really basic regex matching. Oh, that's big enough. Good. Okay, so that's an entire audit. They can be really small. This one's a secret inherits audit. All it does, it looks for places where a reusable workflow uses secrets inherit, which means it inherits the entire secrets context rather than being given a specific set of secrets, meaning it violates the principle of least authority. And then you can also do multiple locations per finding. So you can say like this step calls this action with this set of subfields, and that's why it produces such a nice sort of spanning representation on the command line. And yeah, if you want to contribute, these audits are good examples of things to start learning how to write Lismore audits. Some technical challenges. Like I said, it's all YAML hell under the hood. So one of the questions is, how do we model GitHub's complicated workflow and action contents? It's an extremely large JSON schema that's public, but it's very large and complicated. And codegen support is limited in Rust for JSON schema. Solution is we have this GitHub Actions models crate, which has handwritten data models for every single part of GitHub Actions, which we then use to generate those spans for YAML spanning back to the source. And then that follows the next question, which is, how do we turn these symbolic YAML contents, like this step, back into a span that we render to the user? And the answer is, well, we couldn't with, there's no real span preserving YAML parser for Rust, and also sort of YAML is deprecated, which it still is, and we still depend on it. But we wrote YAML path, which concretizes that abstract path, like job test steps, zero name, back into a source level syntax span for pretty rendering. Okay, takeaways. Stuff's complicated, has numerous security footguns, and most users are normal devs, and they should not be expected to know these things. You shouldn't have to know that GitHub has no sort of permission separation between branches to use caches securely, meaning that they're extra susceptible to insecure defaults. Moreover, offensive security research into GitHub Actions is still pretty new as a field. Really, the first visible public efforts into this stuff started around 2021, and new attacks and techniques are still being discovered. For example, the cache poisoning attack was just last summer. And so, even though I've talked about some of this stuff, it's not anywhere close to the end-all, or will be close to the end-all of action security. And yeah, I said that. It's also simultaneously kind of easy to analyze because it is just YAML, and also very difficult to analyze because there's extremely dynamic inputs like contexts, which can be loaded with pretty much anything, including dynamic matrices that get loaded at runtime. So those kind of things are very difficult to analyze, and we try our best. And as part of that, we detect many security pitfalls, but not with perfect fidelity. And this is in part because of design choices, for example, favoring offline auditing where possible, but also because of that fundamental dynamism. It sort of models normal computer static analysis. You can't do certain things because the program is dynamic and you're static. Okay, so I sped run all that so I could have some time for questions. Thank you all very much for listening. If you want, slides are here. All right. Yes?
Thank you, very nice talk. I have two kind of questions, but they are more or less the same. So, nice tool to use in the command line, but I have hundreds and hundreds of pipelines, so I want to automate this in my pipelines. Any thoughts? Could I do it inside my runners, or could I have a normal action that I run to check the workflow itself?
Yes.
Like exception thing?
Yeah, so the question was, can I use this in my pipeline? And the answer is yes. So I showed the human output. There's also a Serif output that integrates directly into GitHub. And so you can see on GitHub a UI render of these findings.
Okay, and then you run the CLI in your pipeline.
Yes, exactly. Yeah. Yeah. Yeah, Homebrew uses it, so you can use Homebrew as a reference point for using it in CI. Yes?
Sort of a variation of the same question, sorry for that.
Fine.
Could it be possible to write the same kind of audit rules using CodeQL, which is GitHub's own, and then it's super integrated?
Yeah, so the question was, can we rewrite the same kind of rules using GitHub's CodeQL feature? And the answer is they have. GitHub 2 weeks ago introduced beta support for GitHub Actions auditing with CodeQL. And I will say this, because I wrote this tool, CodeQL is a much better fundamental system than what I wrote. So if you want a system that is fundamentally built for static analysis, check it out. The downside is that it's CodeQL, it's big, it's complicated to integrate. So there's some trade-off there. Yes?
If you look at GitLab CI, that's all observed very similar with this YAML files. Are the problems the same, or is it something away?
Yeah, the question was, is GitLab CI similar? And the answer is I have no idea. Maybe. I would love it if someone looked and sent me patches to support GitLab CI. Yes?
So the GitHub Actions APIs as well as the GitHub provided actions are, subject to regular updates. How do you plan on keeping up with those updates?
Yeah, so that's a fantastic question. The question is, how do we keep up to date with the latest changes to, for example, the official actions? My long-term plan is to have a static representation that we can upload via like an HTTP, put it on an HTTP server somewhere, have a static API that pulls it down. So if the default posture of an action changes, clients that don't want to update Zizmore itself can fetch that and basically update the rules. currently it's baked into the binary. So currently, if actions changes something fundamentally, which they haven't really yet, I have to send a new release to propagate it. Yeah. Yes, please contribute. Great, thank you very much. Yeah.
Any fault? I was thinking I built a long time ago a scale of self-hosted action runner, the Amazon GitHub one. But I was thinking, can I, and if you have a self-hosted runner and you put a tool like this into your runner, at the moment you on the pre-hook you get the event, and I think you have access to the pipeline, so you can check the pipeline at that moment before it runs. Maybe start really early warnings.
Yeah, that would be really nice if you could do that. Yeah, preemptively. Yeah, that's a fantastic idea. I mean, if you control the runner controller, then it's
It's about 50,000 jobs every day.
You guys are doing some really fantastic work.
Oh, thank you. I appreciate it.
But yeah, thank you, man. Do you mind if I connect you?
Sure, yeah. Well, I don't have LinkedIn, though. That's easy.
Okay.
Yeah, I have a business card or Mastodon.
Yeah, you won't get it.
Yeah, I'm getting them. Easy to find.
Yeah, you're happy to.
Thank you.
That's something. Did you find anything else today, or have you been?
I don't know. I was like rest 5. I was for some like bug hunters and it was interesting. Benchmarking of risk 5, which is less interesting than processing like or benchmarkers.
Yeah.
I was on the post-quantum OpenGP.
Yeah. Was there anything new, or I think that
Nothing so special. Like, it was just summary of those standards that they are proposing.
Have enough of people for today.
Yeah, it's exhausting.
You were here like for a long
Yeah, the most of the day. I had like, I don't know, 2.5 hours break.
not forget my
Backpack is here.
hopefully the speaker is not doesn't get stuck on the restroom. So Rabja, how do you think how long do you think it will take for the
Hopefully not that long.
equipment guy?
Hopefully not that long, like, I don't know, half an hour max.
Richard is
Back to work, and I can do the sound check.
touch it. Say something. Hello, hello. Can you hear me?
Very good.
Nice.
And you will have 25 minutes.
Yeah.
And I can do this countdown. And preferably we have 25 minutes, but 20 minutes for presentation and 5 minutes.
Yeah, perfect.
So I'll count down to 20 minutes.
Yeah, sounds good.
Hopefully we'll have some.
Yeah. So I'm ready to start.
4 minutes. No, we need to start on time.
Oh yeah, of course, of course.
For recorded.
Yeah, yeah.
4 more minutes.
To tell some jokes.
Oh, I'm super bad at jokes, and it's late of the day, and I'm tired, and I feel like you're probably very tired as well, so. Yep.
Fredrik Skogman.
Yeah, that's good, that's good. Fredrik Skogman in Swedish, but yeah, very good. I heard worse.
So, welcome to the last session of the Security Dev Room. Let me introduce Fredrik Skogman with his talk on enhancing artifact security with GitHub artifact attestations.
Thank you. So yeah, my name is Fredrik Skogman. I work at GitHub, and my team is primarily focusing on supply chain security, and I'm an active maintainer in a lot of open source security related things like SigStore and Update Framework. And also thank you very much for coming. I know it's super late. You are probably tired. I'm tired, so I will try to run this as fast as I can. Speak up. I will. Oh, sorry. Sorry, this is on me. There we go. So, yeah, I would like to talk about artifact attestations. So this is a feature that fairly recently out. So it allows you to provide a way to guarantee integrity from the build step to delivery for everything that's built on GitHub Actions. This way we like to offer a very simple way to sign all this open source stuff that you're building. So it's been around since summer of 2024, and the work started in 2022 when we were doing a similar way for open source NPM packages to provide signed build provenance for everything that's built on for NPM. And of course it's free for open source to use, so I encourage everyone to use it. And early adopters include Homebrew, so huge thanks to William, previous presenter. So they've been working very hard with us to try it out and make it working. And I'm super excited that all bottles on Homebrew are now signed and built with provenance. Although the Homebrew is still in beta, so we're working on them to kind of clear out a few issues that they're experiencing to go full GA. So to kind of describe the problem, I would like to start a little bit with sort of typical signing, how it happens. Like you have a typical build pipeline. You build something from source code repository, you put it into the registry signs it, and then the user can download it from the registry and they can verify it hasn't been tampered with from the registry. The problem is what went into the registry in the first place. It's very hard to tell. You just know that it was signed by the registry, but was it a release? Was it a dev build? We don't really know. Maybe it was a malicious artifact being put in the first place. And basically, we're lacking some context of the artifacts when it comes from the registry. You can try to solve it by pushing signing sort of further to the left. But given a lot of the solutions out there, like it creates a problem around managing the PKI. Like it's kind of complicated, and not all open source projects have the resources to run like a fully complete PKI system. So that's kind of what we are trying to simplify with this. So with artifact attestations, when you're building something in the action, it's signed automatically by the system, and it's not just signed, it also extracts a lot of metadata around the build, like which repository was it coming from, what are the commit ID, and so on. So basically, we're capturing the context around the build, and via that, we are also including like the exact build run. So we're creating like a paper trail, tracing the specific artifact back to a specific workflow run. So with part of this, we are hosting an entire PKI platform, and we're also doing it by relying on workload identities instead of like human identities. So that gives us a way to kind of simplify the policy processing around it. And the great thing about it is that from a developer perspective, you don't need to manage any key material at all. Like everything happens automatically by the system, which I will of course describe. So, rough, yep?
Is it cool if I ask a question?
Please wait, if possible.
Yeah, okay.
Yep. I will get sidetracked otherwise I forget what to say. Yeah, so some of the components, like we have the actions, of course, that you can use in your workflow. We have a CA and a PKI, an attestation store to capture the metadata that's generated during the build. And then we have the GitHub CLI that can be used to run policies around your artifact. And then there's an integration with the policy controller from Sigstore, which is a Kubernetes admission controller. So you can use the same thing to secure your workloads in like Kubernetes way. So everything, well, almost everything is done fully open source. Like we want to meet the community where it is, so we avoid to build any custom things that only work with what we're doing. So we're teaming up very much with Sigstore, Salsa, Intero, and Tough. So a quick introduction is that Sigstore is an open source project that aims to simplify signing and verification for everything. And according to the Sigstore project, they are trying to be like the Let's Encrypt for digital signatures. And very interesting with Sigstore is that it's not just a lot of source code repositories that you can use. SIGSTOR is also a public good instance that anyone can use, and my team are part of that operations as well. Like, we are wearing the pager for the public good SIGSTOR instance to make sure it's operating as smooth as it can. For describing the metadata around the builds, we are relying on something called SALSA build provenance, and it's a standardized format for distributing metadata for builds. And to kind of ship them around and tie them to the specific artifact, we're using in toto attestations, which sort of create that link between a subject and some metadata, or predicate as it's called in toto. And then we have the update framework, which is a framework for securing upgrades over untrusted channels. So we are relying on that to manage the trust root, like the root certificates and public keys, etc. So we're using it to manage it and to distribute it to the clients. So a simple overview of the system is that when you're running a build, if you're using attestations or artifact attestations, the system first collects the metadata required, like, as I mentioned, repository, git commit, workflow run, the actual workflow file being used. It then extracts an identification token from the actions that uniquely identifies the build, and then we use that to request a signing certificate from Fulcio. And then when you have the signing certificate, we can sign the provenance and we can put it in our attestation store. And then clients can, via the update framework, get the latest version of the trust root, fetch whatever attestation they would like, because they might have a file and they can compute it, digest and query our store, and then they will get all the matching attestations for that and then run whatever verification they would like to use. And it doesn't have to be, in this case, the GitHub client, like it could be Cosign, or basically any SIGSTOR client will work here. So to avoid the burden of relying on developers managing private keys, SIGSTOR is heavily relying on something called ephemeral keys or ambient tokens, or you might also have heard keyless signing, which is of course just a gimmick, like keys are definitely used. So the way it works is that you create an in-memory key pair, and then you send the public key of that together with identity token describing who you are to the CA, who then verifies the identity token via federation to the identity provider to make sure you're not lying. And then it creates a short-lived certificate that's only valid for 10 minutes, binds it to the public key, and then sends it back. Then you can sign via that certificate. And because the certificate is only valid for 10 minutes, you need to think about something to simplify the verification, because you can't rely on the typical certificate verification where the certificate has to be valid during the time you're verifying. So what we're doing here is that we either reach out to a timestamping authority, or in the SIGSTOR public good instance, we are using a public append-only transparency log that also gives us a timestamp. So we can get a counter signature and then store that together with the original signature. And then when you're trying to verify this, you can verify the timestamp of the signature when it was made, and that way you can see, like, okay, this signature was made during the time the certificate was valid. And this greatly improves the risk of a key compromise, because let's say someone manages to extract a key from the memory, it's very unlikely that they will do it and compromise a full attack within the 10-minute window. So yeah, the benefits of using SIGSTOR here is you get identity federation out of the box. So you have a system that kind of vouches for your identity. You don't need to manage the keys. And especially for artifact attestations, we rely on workload identities instead of human identities. So the identity is basically the organization, repository, and the workflow. So you don't need to understand who is the maintainer of this package and something like that. You can kind of look at where should this thing come from, or is expected to come from this repository. So as I mentioned, SIGSTOR operates one instance. At GitHub we operate a private instance. The public instance from Sigstore is free for use for anyone, but you need to think that everything that's being signed is also put on a public transparency log, so if you have privacy concerns, it may not be the right place. The instance we are running at GitHub is completely compatible with the public good, so every tooling that you have will work with both of these instances. So, the Salsa build provenance, so it's a JSON specification for the format capturing a lot of the metadata. As I mentioned, we have the basic stuff like repository, owner, and the exact workflow file that was being used. It also contains a reference to like the log of the system, like the build log for the action. And importantly, we also encode the numerical identifiers for the repository and the owner. So that's to make sure you can have a policy to protect against like rename attacks or resurrection attacks. You can of course browse data stations in the web UI, and if you don't like looking at JSON data, you can have like a view that kind of summarize what's in the build provenance doc. And these are of course UX, like it's continually hopefully being improved. It's definitely continually being changed. Right, so if Sigstore is already out there, there is a public instance that anyone can use. Why did we spend like a couple of years doing something on top of this? And it's to get a better experience for the developers. Sigstore is mostly concerned around signing and verification. Sigstore doesn't really know what a Salsa build provenance is. Sigstore does not provide a solution for storing or discovery of attestations. So those are the things that we have added on top of the existing Sigstore components. Yes. So how to use it? It's pretty simple. If you're on GitHub Actions, you need to add one more step that reference one of the various attest actions we are providing. In this case, it's attest build provenance, and in this example, I'm attesting a container image. And you can see here that also a parameter called push to registry, true, and that means that when the build Docker image is being pushed, we're also pushing the build attestation to the container registry. And the useful thing here is that if you're running, let's say, Kubernetes, you may not want to allow the cluster to communicate with like a random API such as GitHub. So we're putting that attestation next to the image that you already have access to from the cluster, so you can have tighter egress rules. And these actions allows you to attest whatever file that's being produced. It doesn't have to be a container or a package, or it can be basically any digital file, like an SBOM, if you like. So for the verification side, which is the most important, like you should not sign if you're not verifying, then you're not gaining anything. So everything is compatible with cosign, which is sort of the go-to CLI for Sigstore. You can also use the GitHub CLI to verify, or as I said, like if you're running in Kubernetes, you can use the Sigstore policy controller. So when thinking about signatures, I think it's very important to understand just because it's signed doesn't mean that it's secure. The only guarantee we are giving you is that we are giving you a paper trail that this artifact was created here. Safe to run? We can't tell. We can only tell where it's coming from. And of course, you need to follow all the best practices on tightening up your build system, like William's presentation is super good on Sysmore, like very relevant technology to use. On GitHub, we have some solutions like you can rely on, for instance, code owners to separate who can modify the build instructions, or if you want to go for a really secure model, you can have a reusable workflow. And the Salsa community provides a builder for most of the ecosystems out there, like Go, Java, that builds the binary for you, creates the build provenance, and signs it for you. And the benefit here is that you get a complete separation of concerns, because the Salsa builder is in the Salsa org. Like a typical developer doesn't have write access and can modify the build instructions. So that's very useful for a lot of people to kind of make sure that developers can write the code, but they can't modify how it's built. And with reusable workflows, you also get other benefits such as build isolation. The workflow is guaranteed to run on a separate VM. So if you have, for instance, a place where you're running unit test. The test might, for instance, modify the file system that can, change the outcome of the build. So it's a really strong thing to use. I just want to mention 3 recent attacks. Like, it's no grudge against these projects at all for me. It's just that they are very recent and they are very relevant. So in December last year, Solana Web3.js had an attack where someone got a hand on the publish token to NPM. So they uploaded a malicious version that contained, I think it was like crypto wallet stealer, but it's not super relevant. But here, like, if they were using build provenance, you could detect that by modifying, so not modifying, but by verifying the artifact and see that, wait a minute, doesn't have a build provenance, or the build provenance has changed. It's coming from a different repository than it used to be, and that is a strong signal that something may have happened. As William mentioned on the talk before this, Ultralytics had an attack, and in this case, the existence of build provenance proved to be very useful during the forensics, because they can see what was the offending workflow that built this malicious artifact, and that proved like really strong during the forensics. And also, once the first malicious version were removed from the registry, another one was published. And that one did not have build provenance. So if they were verifying the provenance, they will see that the second one didn't have one, which, as I said, like, it's a suspicious signal. The third one is the same scenario as the first one. I just added it there to kind of show that this is a frequent pattern we're seeing. Like, compromised tokens to registries is a common way for people to upload bad packages, and with build provenance you can easily detect if that is happening. So it's getting late, so just going to run through some quick examples of how this can be used. So in this case, by the way, yeah, it's readable. Like, I'm just running the GH or the GitHub CLI to kind of verify that this container image is originating from, in this case, a specific repository. And when you run this, it kind of takes the digest of the image, interacts with the attestation store, gets the matching attestations and verifies them. In here we can see that we're getting information like, yep, it's originating from the expected repository, and we can see a reference to the exact workflow file that was being used to create and sign it. Is this readable? The idea here is I just want to show how it can look like when you're using reusable workflows. So this build creates 3 artifacts. One that's being built directly within the workflow, one creating a debug build via a reusable workflow, and the third one is a release build via another reusable workflow. Because the way you're thinking about signer identity changes a little bit with this. So the first one is the simplest one, is just verifying that this file is originating from a specific repository, and everything looks good. Second one, I'm looking at the debug artifact that was created by the debug reusable workflow, and if I try to verify this, we can see that it's failing, and that is because the identity of the signer doesn't match the expected one. And this is because when you're using a reusable workflow, the signer's identity reference the reusable workflow, not the originating repository. So to fix this, we need to be very explicit that the artifact has to originate from one repository, but it should be signed by another repository. In this case, I'm just saying like any workflow in this repository is good. If you try the same, or if you try to verify with the release workflow for the debug, it's of course failing because that's not the workflow used. If you're using the release artifact, it of course passes. So this is just kind of showing that you need to think about the signer identity. And that is the last slide. Thank you very much. On time.
Thank you, Frederick, for
Yep.
what you were building there. I have been a fan of FOSDEM and also Sixto for quite a while. It's pretty awesome. I have 2 questions. I think they're both pretty the artifacts that you're signing, are you like completely agnostic to what you're signing at GitHub?
Yeah.
For example, if I'm the Lazarus group, I always look for like free infrastructure, let's say GitHub Actions or something where I can leverage them to perform network campaigns. So would there be any kind of checks that you will not sign and publish malware, for example?
No, we currently we don't care really what you're signing. We sign whatever you provide. So the question was around if we have checks for malware and things like that, and we don't. It's currently out of the scope. We're basically providing a link back to the workflow, so we don't introspect the binary at all. Like we sign what you provide to us.
Is that like for a deeper reason that you want to have these two things separated, or is it just like out of scope currently?
It's out of scope, I think, and I think it's a different mitigation attack to kind of introspect and look for binaries, and it goes way beyond signing and working with build provenance.
Thank you.
Yep.
When you mentioned private keys, which are memory generated for signing.
Yep.
Can you talk about what happens if an action runner is compromised? How much are the signing keys, attestation signing keys, or you can request a certificate? How much is that separated?
So the question was around, how do we try to mitigate an attack on the runner to extract the key? And currently, it's not really something that's done beyond the capabilities already in action, and that is one way, for instance, to use a reusable workflow, because you move to a new VM when you do the signing from the building. So that's the preferred way to kind of separate out the concerns. But otherwise, it has to be a full-blown attack on the runner, and as I mentioned, like the certificate is valid for 10 minutes. You need to work really fast.
Thank you very much.
Yep. I think you were, sorry, you're next. Yep.
So, do you think some modules in Bahan, when you create metadata, what things do you include there about the source? If we include, for example, if you fetch code from other repositories, would you include this information in the metadata, like which hashes, which commit IDs did I use?
Yeah. So the question was around basically what data is included in the build provenance, and I think the short answer is that you get the source code that it's being built from. I think that's the primary indicator, and everything is defined by the Salsa team, so that's not something we can we don't want to mess around with that. Like, we want to use what's already decided by the Salsa framework to include in the build provenance. But it's currently the source code, and then sort of via transitive closure you can see what's being pulled from that source code.
By the source code, you mean a hash of the source code?
No, it's only the git commit object.
Okay.
Yeah.
Assuming that the build steps themselves are deterministic, does the metadata give you sufficient information to be able to reproduce the artifact?
So the question is, if the build steps are deterministic, does the build provenance give you sufficient information to recreate it? And I would say yes, because the build provenance contains an exact reference to the version of the repository. So you can, for instance, see, okay, this is let's say it's a makefile in there. Then you can look at the makefile and see what steps were being made to build it, and then you can try to reproduce it based on that, if that's your question.
So that's a clear, because you can have network access in there, and there's other external information that can be used in that build process. Like, this is not a reproducible build. Like, the GitHub actions that you're running, that can still do other things.
Oh, yeah.
So this is like, I'll just make sure, like, you cannot be guaranteed to reproduce the same artifact just without information.
Okay, yeah.
Like, build provenance is a very different thing from the
Oh, yeah. Like, we are not making any guarantees at all that it is being reproducible, because, I mean, for instance, if it's a C project, the order of the object files may be, based on the inodes in the file system. So we are not making any guarantees. But if the project is built to be reproducible, that could give you the link to the makefile that was used to build this. But yeah, otherwise we don't make any guarantees at all about reproducible builds.
Two small questions. One is where I heard that you mentioned that GitHub now provides a way to collect and expose the signatures at a common place. Is that correct?
So yeah, they are available via the public API for the repository. So that's how you can query for them.
Okay. And the follow-up was, you mentioned about the private instance of Sigstore. I mean, like, how does that work? Where is the private key stored then in the HSM or?
No, it's the same model. Like, it's still using ephemeral keys. It's just that we are hosting the infrastructure instead of the public good version. Otherwise, they are equally the same. All the actions are exactly the same. So when we are building or when we are creating the provenance, we basically look on the repository visibility. If it's a public repository, we use public Sigstore. Otherwise, we're using ours. But otherwise, they are technically more or less the same. Yep.
So that you are attesting Docker images, NPM packages, are there other registries that are supported?
Yeah, for Docker images in specifics. Yeah, so the question was if other repositories for Docker are supported, and the answer is yes. I don't have the full list in my head, but I think virtually every container registry out there we are supporting, and when we are uploading the build attestation, we are probing for compatibility with the Refers API. So if you support the Refers API, we rely on that. Otherwise, we use, it's called like a tag hack that Sigstore invented to upload a signature next to a container that, in a registry. So yeah, I would say probably everything out there, at least that I'm aware of, should support this. Yeah. Yep.
And what about other packages?
Packages.
Yeah.
Yeah. So we did the work for NPM. PyPy is using sort of their own version of build provenance. Homebrew uses it, and I think, Maven are doing something similar with Sigstore. They're not using build provenance, but they're relying on Sigstore signatures. Ruby is working at it. So those are, but yeah, I think it's also important to understand the difference between a Sigstore signature and a build provenance, because a build provenance is, metadata around it, whereas Sigstore is just signing your package without the extra context. So a lot of ecosystems are looking at Sigstore, and we're of course hoping that they will start to use Salsa provenance as well, because I think that gives you more information when you're doing a policy evaluation.
I'm actually working on Erlang and Elixir right now.
Oh, nice. Super happy to hear. Thanks. Yeah.
Thank you.
Yeah, thank you. We made it on time.
The question was actually about the root of the private instance of Sigstore. Like the public instance uses the update framework.
Yep.
But if you create a private system, do you use the same framework? Then who has the?
Yeah, we're using the same technology for the private. Yeah.
All right.
But of course, we have different people running it.
Okay, internally.
Yeah. But the technology is exactly the same.
I know that.
Yeah.
Thank you.
Yeah, thanks.
I just have a small question. Is timestamp authority of GitHub publicly available?
Sorry, if
is the timestamp authority? So I'm working in William's team, and we develop as a signing timestamp support for Sigstore, and we can't test it against GitHub.
Yeah, so the timestamp authority is public available, but it's not officially announced as public available.
Okay.
So
But
you
is
can use it
there
today,
link?
but I cannot promise it's going to be available.
Yeah, but just at least for our own tests. Right?
Yeah.
What about stability of all the running system? Do you promise that these, like a blockchain, that if you change it tomorrow, it will be difficult to verify?
Yes, so we are, it's a large topic and a short amount of time, but we are publishing all sort of older versions of our root certificate chains. So they are it's basically we are appending newer and newer versions of the certificate chain. So the one that we used, let's say, 5 years ago, even though it didn't exist, they are still available, but they are limited. Like these are the certificate chains that were used 5 years ago.
But like the Sigstore PGI version, will you role that, because it's a running transparency blockchain, right?
Yeah.
So if you reset it, everything will go away. Are there any public promises that
Yes.
this is the this is the golden one?
Yeah. So currently there's only one like RECOR version. Yeah. And for key management, for that it's the same. We are, because I'm part of maintaining the trust root for public good instance as well. So we are doing the same there. Like we are providing sort of a structure around time that says these are the log that was active during this time period, and this is the public key.
So you could.
Yeah. So when we are doing sharding, which we do like sort of annually for RECOR, we're just announcing like this is the new URL for the log, and this is the key that's being used by this shard. So that's sort of. So it's basically just.
I think I'm gonna like leave you alone for the evening. I'm gonna like follow up on that. You know, like what is going into what is being signed by GitHub infrastructure. I'm gonna send you a connection request on LinkedIn.
Yeah, perfect.
And then we can chat there. It's like Kyle Kelly is in your team. Madison Oliver is.
Kyle Kelly started last week.
Okay, fantastic, cool. Yeah,
so
he's also very interested in that question.
He joined the team last week.
Yeah.
So he's still doing onboarding.
Okay, nice, cool. Because I'm interested, like, what do you sort of like strategically think can be done, like on GitHub side to make sure that sort of malware wouldn't be packaged?
Yeah.
That would be kind of like a nice conversation. I would like to have with you.
Definitely.
Thank you for the talk.
Yeah,
Awesome
thanks.
work.
Yeah, thanks.
Appreciate it.
Thank you for your work.
Yeah,
I'm interested in using this for signing the RIS5 toolchains that we use GitHub Actions to build. On the RIS5 repo, and I was wondering, do you have documentation somewhere that I can use that?
Yes, there is. We have documentation and we have blog posts around it.
So there is a link in your talk?
Sadly, it's not. But if you search for if you Google or whatever favorite search engine you have for GitHub attestations or GitHub artifact attestations, you should find it. Otherwise, I should have put the documentation links, but I didn't.
So I will find it on Google. It's already online.
Yeah, it's online. This has been around since.
And I can include it in my workload, like something. Like I do for cache or whatever.
Yeah, you can. I would say it's easy. Like you add one step, reference the artifact you want to attest to, and then it just does it for you.
Thank you very much.
Yeah, you got it.
Hi, I have one question related to SysStore and especially the 10-minute key, lifespan keys. Because a couple of months ago I was thinking that, okay, you have to use the limited lifespan to 10 minutes for tighten the security. But have you considered the option that if you instead of just giving the network compliance or Kubernetes